We have two speakers today. The first is Andrea Bertozzi, and the second is Mark Girolami, who is here. There he is. He'll be speaking momentarily. Let me tell you very briefly about Andrea. Andrea Bertozzi began her career at Princeton. She did her undergraduate, master's, and doctorate at Princeton. When you start something good, you stay with it.
Pretty much.
She went to Chicago briefly. Well, not so briefly, but to begin her career. Yeah. Then she went to Duke for a little while, and then she joined UCLA about a little over a decade ago. She's been at UCLA for quite a while. Those of you who know Andrea Bertozzi's work probably know that it would be impossible for me to tell you very much about Andrea Bertozzi's work other than in very broad strokes. She has nearly 200 journal publications. She's worked in very, very many different areas. Roughly speaking, she does very timely work that connects between discrete problems using the continuum limits that we can model with PDEs well, and then linear algebra to model the discrete nature of the problems. It's a fantastic recipe. And today, Andrea is going to tell us about geometric graph-based methods for high-dimensional data. Over to you, Andrea.
Thank you. So it's an honor to be giving a Turing lecture here at the New Turing Institute in London. I visited London many times, and it feels a little bit like home to me compared to all the cities on this side of the Atlantic. I grew up in Boston, Massachusetts, so that might make some sense. I always tell the cab drivers in London that for some reason I can understand absolutely everything everybody says in the UK, which is not true in the US, just for reference, right? There are parts of the US where the accents I find difficult, but not so much in the UK, which is unusual, and I don't know why, because I clearly have an American accent myself. But anyway, it's a pleasure to be here, and also thank you for letting me share with you all some recent work from my group at UCLA. This is one of those stories I like to tell my students, that you never know when an opportunity is going to present itself for research that will lead to a very large body of work, almost by a chance encounter. And that is my story with this piece of work, and it really started with a half-hour conversation with my collaborator, who at the time was not a collaborator, Arjuna Flenner from China Lake, who showed me some work that he was doing involving similarity graphs for big data. Up until this point in time, I had not been working on machine learning problems. I had been working on PDE methods for image processing, and of course, if you come into UCLA, at least back when I came in 2003, as somebody with a background in interfaces and fluids and nonlinear PDE, it was almost impossible not to get into the excitement of the image processing that was going on at the time. So I learned a lot working with people like Stan Osher and Luminita Vese and Tony Chan. And those ideas kind of germinated in my head, an idea to try to take some of these approaches from low-dimensional image processing and bring them to problems in high-dimensional data, specifically in a graphical setting. So you see the word graph here. Okay, and so, but I had ideas, but I knew that I didn't know everything that I needed to do what I wanted to do. And I happened to run into Arjuna, he said, come to my office. I was visiting China Lake. He said, let me show you what I'm working on. And what he showed me was kind of the missing piece. So I like to tell my students and postdocs, I said, you know, if you're into research and you have ideas, it's like you have a jigsaw puzzle with only half the pieces. And you've arranged them in some way in your head, and sometimes you meet somebody with the other half of the pieces. And if you do that, you really want to work with them, right? You want to make sure. So I said to Arjuna, I said, listen to me for 20 minutes. Just don't talk. Just give me 20 minutes to write on your board. I'm going to sketch a paper that we're going to write. And then at the end of the 20 minutes, tell me yes or no, right? And so thankfully, he said yes. And so we wrote a paper. And that paper led to now, I don't know how many, I think 5 actually now, because one of my students, and I have another student that's missing here, but 5 PhD theses and a master's thesis, and now 3 new students, and a lot of collaborations and lots of people now who've been involved, including someone from this side of the world, Mason Porter, who is also from Los Angeles originally and will be moving to UCLA this summer. So, I mean, and I have to say that had I not done that original work with Flenner, I probably wouldn't have worked with Porter, and who knows if we would have recruited him to UCLA. So lots of, this one 20-minute conversation has triggered this huge avalanche of events in mathematics research. So that's one sort of little anecdotal story. So now what I want to do, I have to figure out which button to push. Let's see, this one. All right, so what I want to do quickly, because I think we're doing 45 minutes, right? Okay, so I'm just going to kind of quickly tell you some of the background that inspired the new work. These are, these are 3 models from image processing for segmentation. You're looking at a lot of math here. They're models where you basically have a curve in the plane, and the plane has an image, and you want to figure out where you're going to put the curve so that it's segmenting things in the image. And so the curve is gamma. Here's gamma, the curve, and here it is here. And here you don't know where it is. So these are variational models where you have an energy functional, and you're trying to figure out the best values of the arguments of the energy so that you minimize this energy. So we have to figure out where to put the curve, and in this case, in the Mumford-Shaw model, you have to figure out a piecewise smooth representation of the image. That's U. And so here we have a least squares fit to the noisy data F. Here's the smooth component away from the curve, the boundary, and here's the curve. So this is the length of the boundary. This is, all the geometry is in this one little, seemingly innocuous term, the length of the boundary. This is a model that involves snakes. So Z is a parameterization of the curve in terms of a parameter S off an arc length. These 2 terms together do not give you the length of the boundary, but they control the length of the boundary, written out parametrically in terms of that parameter. And all of the, so this is the geometry term right here, and all of the content of the image is bundled up into this one term here, which basically is a big fancy well that measures kind of crudely where the edges are in the image using some kind of edge detector. And then it puts wells so F basically is going to let Z fall into the wells. So this is the snake method. And then this bottom method, which is due to 2 of my UCLA colleagues, Tony Chan and Luminita Vesse, is basically just a simplification of Mumford-Shaw, but it's a very, very astute simplification of Mumford-Shaw. It's a piecewise constant representation of the image. So instead of having a piecewise smooth U, all you have are 2 constants, C1 and C2. So the least squares fit gives you these 2 terms here. The smoothness term, well, the gradient of a constant is what? 0. Good, so that term goes away, and the length of the boundary. So all the geometry is in this term. So there's a lot of geometry in these models because you're trying to shrink the length of the boundary, but you don't quite see the geometry staring you in the face. Now, if you want to minimize these energy functionals, then you start to see the geometry because you have to worry about this geometric term. And so okay, so in case you're wondering, what does the Mumford-Shaw versus the Chan-Vesse model look like? Well, you take an image like Pascal. Right, so this is Pascal. Pascal was a student at UCLA. There he wrote an IPO paper, Image Processing Online. If you have students who like to play with image processing stuff, this is an online journal where you can upload your own images and run the code in real time on your images. So that's kind of fun. So Pascal with Mumford-Shaw, piecewise smooth. Pascal with Chan-Vesse, piecewise constant. So you see what you get with those models. Okay, so remember, in both of these cases, the boundary, which is the region between where you see the jump discontinuity, that's been smoothed. I mean, there's a lot of noise in the image, and that's all gone because you can see it's fairly smooth. And that's coming from the fact that we have this regularization parameter. This makes the problem well posed because you have to put in a term that controls the regularity of the boundary, and that's these 2 terms here, and I'm not going to focus so much on the snakes. Okay, so these are Eulerian methods. Okay, so now length of the boundary. Let's talk about the length of the boundary and another way to measure that. So if I have, I have my data and I have my curve, and the curve surrounds a region omega. So I can now write, and there's the curve gamma, and I can now write that I can now write this curve gamma in terms of a global function u, which is just the characteristic function of omega. So the boundary of omega is gamma. U is the characteristic function of omega. And if I want to measure the length of gamma, the perimeter, I can measure that by simply computing something about u. What is the something? It is the total variation semi-norm. Okay? So this is more geometry. Total variation of u gives us the length of the perimeter of gamma. By the way, this is the L1 norm of the gradient. So for people who know compressed sensing, you might wonder if there is some sparsity constraint that you get out of this. And the answer is, of course there is. By shrinking the length of the boundary, you're basically looking at a sparse solution in terms of the amount of edges in the solution, right? So it's sparse. It is sparse, but it basically gives you an equivalent geometric formulation. Okay, so you're wondering, what does all this have to do with big data? Be patient, I'm getting there. And the next thing I want to do is I want to write down, I'm now going to do the thing that if you're at UCLA and you do this thing, Stan Osher has a heart attack, not really, but almost, which is to take the L1 norm and turn it into an L2 norm. Okay, and how do I do that? Well, that's kind of crazy, you might think, because I'm removing the sparsity. So here's the L2 norm of the gradient, but I have a small parameter in front of it. So the L2 norm is going to bring back smoothness in the solution u, but I'm going to try to keep the smoothness from being too important by putting in a double well potential. The double well potential is forcing you to take a binary structure like we had in the original formulation here. And this object here has a name. It's called the Ginzburg-Landau functional. And if you go back a few decades in nonlinear PDE, you discover that there's beautiful theory proving gamma convergence of the Ginzburg-Landau energy to the total variation semi-norm. So the two are related despite the fact that one has L2 and the other one has L1. And it's this connection that we want to use for solving data classification and segmentation problems. But we're going to do it not in Euclidean space, but rather we're going to put this entire structure in a graphical setting. Okay, but before we do that, I need to show you some more PDEs, because that's what I do. So if I take the Ginzburg-Landau energy and I do a gradient descent to try to minimize it, I get this beautiful partial differential equation called the Alencon equation. So this is the time evolution of u. The first term from the L2 energy gives me the Laplace operator with the small parameter in front. The double well gives me a large parameter in front of the gradient of the double well, the first derivative of the double well. So you can think of this as an evolution equation that is trying to simultaneously smooth u from this term and simultaneously force you to have one of two binary values. And they fight with each other. However, because of the scaling, they fight with each other in such a way that when epsilon gets very small, the dynamics of this gives you what's very close to motion by mean curvature of the interface, which is a curve shortening dynamical geometric motion. Okay. So one more thing, which is, and this is also work by my colleague Stan Osher from about 25 years ago with Merriman and Benson. It's called the MBO scheme. And the idea is basically, in a nutshell, if we look at the Ginzburg-Landau evolution for the Alencon, you see you're fighting two terms, the heat equation and a term that's forcing you into one of two values. And now you can implement this forcing term directly without doing any evolution at all by simply thresholding the solution. If you're closer to one value, make it that value. If you're closer to the other value, make it that one. That's called thresholding. So they had this brilliant idea that they could do motion by mean curvature by alternating between the heat equation dynamic and thresholding. And in fact, it does work, and you can prove that. And so that's called the MBO scheme for motion by mean curvature, where you alternate between a short time solution of the heat equation to give you a blurry answer, and you take the blurry answer and then you threshold it to get a jump discontinuity. And the way that works for the curve is you start off with a curve. You take the characteristic function whose boundary, whose boundary for its support is that curve. That characteristic function, which is shown here, is the initial data for the heat equation. You solve the heat equation for short time. It smooths this initial characteristic function. You threshold the smooth thing, so you're going to get a new characteristic function, which has a new boundary, which is C2. Okay, so that was a lot. That was a big mouthful, but the steps are pretty simple. And you can repeat this, and you get another curve, right? And if you follow the curves, they're basically approximating motion by mean curvature. And if you think about it, the only algorithms that we need to do this are basically the heat solver. That's it. Thresholding is trivial. Okay, that's about as simple as you can get. So the only thing that's hard is the heat solver, and of course for PDE, if you're looking at Euclidean geometry, 2D, why not just do something simple like the fast Fourier transform, which gives you a very, very, very fast and efficient heat solver, assuming your grid is uniform, which it typically is for image processing problems, right? So this idea was turned into a beautiful image segmentation algorithm for the piecewise constant Mumford-Shaw model by Esadoglu and Tsai, also former UCLA people, and that was published in 2006. So that's 10 years ago that this paper came out. So I was watching all of this with MBO and everything, and I started getting ideas in my head that maybe we should be thinking about these things for big data, right? Maybe we should be taking these beautiful PDE models for minimal surfaces with the Laplacian, with pseudo-spectral methods that are used to solve the heat equation, that use the fast Fourier transform. All of these ideas, maybe we could port them to graph clustering problems, okay? So now, instead of solving a continuum minimal surface problem, we want to solve a discrete minimum cut problem. And by the way, if I tell computer scientists I've got a great algorithm for this, and they laugh at me because there's a million algorithms out there for solving minimum cuts. Okay, but I claim that we have something that can do things that other methods can't, and it's leveraging directly a lot of work that's gone into linear algebra for the graph Laplacian. And what we're doing here is for the graph Laplacian, which I'll explain what that is, we're going to be projecting onto eigensubspaces of this linear operator. We're going to be using some sophisticated numerical linear algebra. We have a couple of different methods, one for non-sparse matrices, which is a Nystrom extension, which is a beautiful idea that was published in a paper about 12 years ago. And also for the sparse case, we use a Rayleigh-Chebyshev method due to my colleague Chris Anderson at UCLA, and he published that in 2010. So these are methods within the last 10 or 12 years. A big difference between this side and this side is that we only need a small percentage of spectral modes rather than taking essentially all the modes, which is what you would do in Euclidean geometry. And people say, why can you do that? Well, if you're looking at an image processing problem and you're using classical differential operators, the differential operators here have absolutely nothing to do with the image, right? They're just differential operators, right, from calculus. They don't know anything about the data. In contrast, our graph Laplacian here is going to be constructed from the data. So there's a lot of information already encoded into that linear operator. And so we get to leverage that. Okay, so now how do we take our data and put it on a graph? Well, this is also an idea that's been out there for a little while, and we're going to look at what's called a similarity graph. So what that means is every single node on my graph, so a graph is just nodes with connections between them, and you can have directed graphs, undirected graphs. We're going to be looking at specifically undirected graphs, but weighted graphs. So that means that every node is connected to some other subset of nodes, and the connections are symmetric, and the connections have a weight attached to them. So the connections are not 0 and 1. If you were looking at like Facebook Friendship Network, that would be a binary set of weights. Here the weights are actually weighted, and they depend upon how similar are the pieces of data at the nodes, right? So I'm going to take the weights to have a formula like this, where I have data at one node and data at another node, and I have some metric that allows me to compare how similar are those pieces of data. And so you see, if the two pieces are identical, then my norm should be 0, and then the exponential is 1. So if they're identical, I have a weight of 1, which is the biggest weight I can have. And if they're quite different from each other, then this norm could be very big, and so my exponential with the minus sign is small. And so a weight close to 0 means that the data is not similar at all. And that's called a similarity graph. And if we were to construct the full graph for an entire data set, we would have order n squared calculations to do to compute all the weights for n pieces of data. Okay, so that's an n squared calculation, and I'm going to come back to that. That is not very good. Okay, so one of the reasons why I had to wait to find somebody to work with who knew a lot about the linear algebra is exactly for that reason. And this idea, this Nystrom extension idea, allows us to get a lot of information about the graph Laplacian in order n calculations rather than n squared, because we don't actually compute the whole graph. We do random sampling. Okay, so that's, so now what can you do with the similarity graph? Well, you can study data and you can try to see, can we segment it, for example? Can we classify data? So you can take some toy problems. Here's one toy problem we worked with, which is the US Congress. So this joke doesn't go as far here as it might in the US, but I think you'll get it. So we don't use 2015 voting records of the US Congress because we could probably classify them with one vote, right? That's the joke. So we need something a little more interesting. We used 1984 data where the votes were a little less obvious. So that's a simple example. The House of Representatives in the US is 435 members, which is not a very big data set. So you can do order n squared without a problem for that data set. A much harder data set is the non-local means graph from image processing. This is a graph where every pixel in the image is a node. And for each pixel, you're actually looking at a patch neighborhood around that pixel. And the pixels could be big, like they could be hyperspectral rather than RGB. But whatever it is, you take a patch around that pixel, and that gives you a feature vector. And that entire feature vector is the data associated with that one pixel node, right? So it's a lot of pixels. So if you think about a sort of 256 squared image, you're going to have, what, 40, 50,000 pixels, and that is n. And so the number of connections is n squared, right? So that would not be a calculation that you would want to do. So typically when we look at the non-local means graph, we either have to come up with a sparse representation using the location of the pixels, or if we don't want to do that, and I'm going to show you an example where we really don't want to do that, then we use the Nystrom extension. Okay, now, once we have our graph, what we'd like to do is we'd like to do machine learning problems, semi-supervised and unsupervised learning, which means that we're going to have to come up with a model for that based on the graphical structure. And the model that we have been looking at involves minimizing, so they're variational models, just like the examples I already showed you from image processing. And if you remember, the examples from image processing had the length of the boundary between the regions as a regularization parameter. And so we're going to have a similar regularization parameter here, but it's going to be the minimum cut. We're going to try to minimize the size of the cut. So how do we do that? Well, remember from image processing, we were taking, instead of looking at the boundary, we started looking at a different object, which is equivalent, which is a characteristic function, right? That tells you whether you're inside or outside. So if I have for the graph, we call that the assignment function. It assigns a color to every node. And so if I take an assignment function f, and I want to measure the size of the cut, well, what's that doing? Well, if I color some of my nodes black and some of them white, I need to sum up all of the weights between unlike nodes, and that tells me how big is the cut. Okay? So I can write that as a formula for f, and I can write it here as the sum of all the weights of the absolute value of fi minus fj. And you notice that if you have a node I and a node j with different color f, then this difference is going to be non-zero, right? It's going to be some non-zero number, and I will pick up that weight in the sum. But if I and j have the same value of f, then this difference will be 0, and I will not pick up that weight. So this is just a formula to measure the size of the cut when I'm defining my cut in terms of an assignment function f. Okay, so that's the comparison. And this has a name. This is the total variation for the assignment function. It's the graph TV. Okay, so I'm using that with a lot of purpose because we're going to take this as our regularizer for the semi-supervised learning problem. Now, these graphical ideas have some history already in image processing. I'll just mention very quickly, going back to about 10 years ago, work of Boati's Colin Morell and my colleagues from UCLA, Osher and Gilboa, developing the non-local means functional for imaging applications. It's very effective for things like image and painting and applications with texture. But the algorithms that they developed, this was prior to split Bregman. For those of you who know what that is in compressed sensing, it's a well-known method for L1 minimization. And by the way, this is an L1 minimization problem, okay? So these methods were slower, and that was one of the speed was basically a big issue for them. But they weren't really thinking about these problems quite in the context of general machine learning. So that's another issue. It's amazing looking back 10 years later how far compressed sensing, how far that field has come in 10 years. It's really quite something. I'll say more recently, looking at a special cut problem. In particular, there's a problem called the Cheeger cut, which is, I haven't written the formula down, but it's a minimizing a cut with a ratio, so you have a balance between the sizes of the two sets. So there's been a bunch of work also by people connected to UCLA looking at compressed sensing methods for the Cheeger cut problem. And those are a little different from the algorithms I'm going to present, but I did want to mention this work. Okay, so my paper with Arjuna was basically started with Arjuna and I discussing how to use the Ginzburg-Landau energy to do semi-supervised learning. So let me tell you what that is for the graphical setting. So first of all, I have a weighted graph, so I know the weights. I also have, for every node, I can compute the sum of all the weights coming into that node, and that gives me the degree of the node, which I'm going to call D. And if I write down this linear operator, which is on the diagonal is the degree, on the off diagonal is minus the weights, that's called the graph Laplacian. Okay, and so you might think, well, what does that have to do with other Laplacians that I know? Well, I know there are experts here in numerical analysis. There's one right there, but there are more. And if you take, so for example, if you took the 4 regular graph in 2D and you computed for that particular graph, if you actually computed the graph Laplacian, you would get something that looks quite a lot like the 5-point stencil finite difference operator that we all know as an approximation of the continuum Laplace operator, with one major difference, which is the sign. Okay, it would be a negative definite operator in numerical analysis. Here it's positive definite operator, and that's a convention. Okay, that's just a convention that the computer scientists like to think they invented this separately, right? We all know they didn't, but of course, they like to pretend that. So they like the positive definite operator, which is what we have here. So once you have this linear operator, you can take an inner product of some function u. So u is defined on the graph. On the node, this is going to be our assignment function, by the way. This is going to be our candidate assignment function. And you can take the inner product of u with L of u, and that has a name too. That's the Dirichlet energy, and it looks like this. And for people from PDE, this is the graph analog of something that, for those of you who know Sobolev spaces, it's the H1 semi-norm. For L2 Sobolev spaces, this is the graphical analog of the H1 semi-norm. If you don't know PDE, just pretend I didn't say anything for the last minute. Okay. All right. So that's our Dirichlet energy. By the way, for some kinds of data, you don't really want this one. You actually want to normalize L, and this is a popular normalization. It's a symmetric rescaled graph Laplacian with a scaling that depends upon the degree. This is the degree matrix, the diagonal matrix D, raised to the -1/2 power. And you can also write it in terms of a random walk Laplacian. So there's a lot of work in the literature that I'm going to kind of wave my hands at, but then tell you what we did. So what we did, and this was our leap, so we literally got up and said, let's take a leap of faith and try something. So sometimes in research you have to do that, right? I can think of my students saying, what the heck were you thinking, right? Because we had no theory at all, but just an idea. So we took the symmetric graph Laplacian, we took the inner product here, we put an epsilon in front of it. We said, let's pretend that's a Dirichlet energy. No, let's pretend that's an H1 semi-norm. We put an epsilon over 2, and then we put a double well, right? So you can evaluate the double well. This is a quartic polynomial, which is exact formula for a double well. So you can take that and evaluate it on each of the nodes. for your assignment function and put a 1 over epsilon term. And then you can put another term, which is the least squares fit to training data. So this is our semi-supervised learning model. Training data. And then these two guys, which look like a mess, our hope was that maybe they were approximating the graph cut. So basically, we're trying to minimize something that looks like the length of the boundary between two regions on the graph, plus a least squares fit to training data. So this looks like an awful lot like the Chan-Bessé model, only it's semi-supervised. So training data means that I have my data set, and I want to break it into, say, 2 parts. And I know, say, 5% of the data, I know exactly which part for those 5% belong in. Okay, so that's semi-supervised learning, okay? So we tried minimizing this, basically using the tools that we already do in nonlinear PDE and numerical analysis, because we know, look, there's been decades of work done on that. So we know really, really, really efficient, stable schemes. So we did that. And strangely enough, the results were really good, right? So this is sort of the turning point here was we ran this example called 2 moons, right? So here's 2 moons. That looks like a really stupid example. It's a bunch of points in the plane. So I'm going to tell you, no, that's not a bunch of points in the plane. That's a bunch of points in 100 dimensions projected onto the plane. Okay, so this really is a machine learning high-dimensional problem. And so the goal was to segment the moons, and you can see the answer with your eyes. And so if you try to do something like spectral clustering, which is well known in the graphical literature, what you're going to do is compute a bunch of eigenfunctions of the graph Laplacian and then run k-means clustering on those things. So for 2 clusters, we look at the Fiedler vector, which is the second eigenvector of the graph Laplacian. And that sure is not going to decompose the data into the 2 moons, right? You can see the cut is in the wrong place. So instead, what we do is we compute a bunch of, maybe like 100, 200 eigenfunctions. It's still not the whole data set. And we then do the Ginzburg-Landau minimization. And we do it by projecting onto the subset of eigenfunctions that we've computed. So when we do the minimization of this problem here, all of the hard part goes into this. These are easy, because you don't see the graph here and you don't see the graph here. There's no information about the weights here or here. It's only right here in that linear operator. Okay? And it's a beautiful symmetric matrix. So there's a lot of tricks that we can use for symmetric matrices, and we did. And so the results are fast and quick because you do it the way you do PDEs and you get good answers. I'll just kind of say in a nutshell. Okay, so we thought this was fun, and we thought we were playing with a one-time thing, and then we discovered that other people's really good code was not as accurate and was slower than our code, which we hadn't even optimized at all. So we thought, okay, maybe this is actually an interesting thing. And so we went back, and with Yves van Gennep, who is now here in the UK at the University of Nottingham, we decided to see if we could make some theory about this, right? Can we prove that this crazy idea is actually directly related to the graph cut? And the answer is you get a theorem. So and it's not that hard to prove, actually. It turns out that working with discrete spaces is sometimes easier than working with the continuum, infinite dimensional spaces. And so here's the theorem. So here's F epsilon. This is a variant of my Ginzburg-Landau model. So this is the Dirichlet energy with a fixed constant, no epsilon, 1 over epsilon times the double well. We can prove that we have gamma convergence of this energy to exactly the graph cut, exactly the total variation energy, which is wonderful. So now we have a theorem that says that the Ginzburg-Landau energy is, at least some variant of it, right, is a good approximation for the graph cut. And that's a new thing. And what is useful about it is the fact that this is an L2 energy here. It's not L1. So we don't have to, well, it's either a blessing or a curse, depending on whether you like L1 minimization methods or you don't. So L1 minimization methods, if you wanted to directly use an L1 method for this, you're going to have to know the weights of the graph. It's hard to do that calculation without knowing the weights. This calculation, on the other hand, because it's an L2 energy, you can basically develop minimization methods that only use the graph Laplacian. And the graph Laplacian has lots of ways to be approximated without computing all the weights. In particular, you can do it using only order n calculations, and that's very, very, very useful and very nice. Okay, this is just the voting. I'm going to skip this because I have cooler stuff to show. But the votes work. I'll just say they work. Okay, so plus voting is not a good topic for this week in the UK, I think. We're not going to talk about voting, right? So okay, so cows. So why cows? So people have come to me and said, you know, this cow image is in like 10 of your papers now. And it's true. And so this is another thing you learn if you write an image processing paper that kind of takes on a life of its own. If you have an image that you use to test your algorithm and other people want to build on that paper, they're going to want to use the same image, and that image is going to go through the literature. So these poor cows have been in a bunch of papers now. And so so people want to know why cow? Why did we pick this image? Well, one thing we wanted to do is we wanted to show that if we pick the cows in one image, that we can find the cows in another image where the pixels in this image could be anywhere. The cows could be anywhere. So in particular, you need a fully connected graph to find the cows. You can't use a graph with just local connections between pixels. You really need to have long-range connections in the graph. So that was one. So we wanted to show off the use of the Nystrom extension. So then you could say, well, you could have picked anything like cows. And the answer is because Arjuna Flenner works for the Navy, and every paper that he submits for publication has to be approved for public release. I don't have to do that at UCLA, he does. And so he wanted to pick objects that they wouldn't think twice about approving for public release. And so right, so this isn't DARPA, we don't have like spy cows, right? So these are just ordinary, right? This is ordinary cows, and the Navy said, okay, you can publish a paper with cows. So that's why, but if you go look at some of my other papers, you're going to see these cows are in like all the papers now, which is kind of funny. I think we would have picked a different image if we had known that, right, 4 years ago. So anyway, there they are. So the point is here that so an analyst might come in with their little pen and go and by hand circle the two cows. And then the point is to tell the code to find the same cows in another image. And so there they are, 1, 2 cows. So that's the segmentation. We call this image labeling. It's a very simple example. Okay, so now, how do we do the energy minimization? That is a non-convex energy, the Ginzburg-Landau model. We actually do it using a convex splitting scheme. And I've done a lot of work on these in PDE for imaging, including a paper with Carol Leschanlieb. So I put that paper up here just to give you another reference for convex splitting schemes from PDE. So you have a non-convex energy, you do a gradient descent, which means you're going to do a time step. There's the delta t, I already multiplied by it out, and there's a minus sign because it's a gradient descent. That's the minus is the descent. Okay, and so there are the two terms in the, so we're taking our non-convex energy, and the magic is you write it as a convex part minus another convex part. So it's convex plus concave. It's called a convex splitting. And by the way, this is not unique. I mean, that's pretty trivial to show that it's not unique because you can always add another convex term and subtract it, right? So this is not a unique way, but there's a special way we do the splitting. Let me get to that. So once you have this decomposition, the point is that you have to pick either the old or the new time level to evaluate the right-hand side. Everything at the new time level would be what we call a backward Euler method. Everything at the old time level we call a forward Euler method. We're not going to do either case. We're going to split it in half. We're going to take the new time level and the convex term and the old time at the concave term. And if you do this the right way, you can get an unconditionally stable method, which is why we like this. And so we do that. And so so it turns out we take the Dirichlet energy for the convex part, which means that at this stage, we're projecting onto eigenfunctions of the first variation of the Dirichlet energy, which is nothing other than the graph Laplacian. So we're just projecting onto eigenfunctions of the graph Laplacian, and there it is, the graph Laplacian. So that's the hard part. Everything else is easy. Okay, so once you see that that works, the next thing you want to do is try the MBO scheme from PDE, only for graphs, because that should be even faster, because all it is the heat equation and thresholding. So it turns out it works like a charm. And this was paper we published with 2 of my PhD students in Sims, I guess 3 years ago. And so it's basically alternating between a forced heat equation. This is from semi-supervised learning. This is your supervision term. And this is the threshold step. And this converges unbelievably quickly, like in a few iterations. It's unbelievably fast. Okay, and again, the punchline is the only point where you need the graph is in the calculation of the graph Laplacian. So if you have a fast way to approximate that, you're basically done. Okay, and so that's the algorithm. And so now here comes the under the hood important stuff, which is the red line, which is that it's only necessary to calculate a portion of the eigenvectors, and you want to do that in a smart way. And so these are the two smart ways, Rayleigh-Chebyshev or Nystrom extension, sparse, non-sparse, depending on whether you have a sparse graph or a non-sparse graph. Okay. So I'm going to skip the examples because they look just like the previous examples, only it's a different algorithm. You get the same results, the cows, same results, right? Like I said, the cows are propagating through the papers, so we had to use them again. And here they are, the sky and the cows, and everything works. Okay, so now multi-class. Okay, so classifying just two classes is not so interesting. In the real world, we often have more than two classes in our data set. So we wanted to show an example or some set of examples with multiple classes and to show that it's really not hard to generalize this. So this is a paper from IEEE TFAMI from 2 years ago. And one of the data sets we worked with is 10 classes. So that's a big jump from 2 to 10. MNIST, those of you from machine learning know this one very well. Those of you not from machine learning, I'll tell you what it is. It's handwritten digits. And it's the shape of the digits. So you're not using the fact that you know it's a 0. No, you're using the fact that it has a shape, and the shape happens to be one of these 10 digits, but of course they're handwritten, so everybody writes the 8 and the 7 and the 6 differently. So we have to somehow look at these shapes and see if we can automatically sort them into the 10 digits. Okay, so MNIST. There are 70,000 digits. And so how are we going to do that? Well, we could do Ginsburg-Landau, but now the double well becomes a multi-well with 10 wells. And you might think, well, that sounds hard because I'm having trouble picturing in my head how you can do 10 wells where each well is completely symmetric with respect to the other 9 wells, right? You have to have symmetry, or otherwise you're going to preference one well over the other wells. And so the way you do that is you take the dimension of the range of the assignment function. So the assignment function in my binary problem is just on the line, right? My assignment function is taking on real values, and I want them to eventually be binary values, but they're on the real line. So here, now what I'm going to do is I'm going to lift this up into a higher dimensional space. I'm going to put this in 10 dimensions. And so in 10 dimensions, I can look at the simplex in 10 dimensions, and I now have wells that are all completely symmetric with respect to each other. It's very easy to write down a 10-well function that has wells in the corners of the simplex in 10 dimensions. So that's what we do. So now U itself is taking on values in 10-dimensional space, but the Dirichlet energy is still the same Dirichlet energy. It's just that U is 10-dimensional instead of 1D. So, and the other thing is that the calculation of the graph Laplacian and its eigenfunctions, that doesn't see the dimension of the space. That's done in 1 dimension, which means that this scales unbelievably well for the number of classes. This is like magic. So I've talked to people in computer science who said, well, you know, all these methods scale really badly if you have multiple classes. And I said, no, this one actually scales even better, right? It's essentially sublinear with the number of classes because you do the calculation of L once without seeing the number of classes. And you only see the number of classes in the optimization problem itself. So that's pretty cool. I mean, it's for people who come from geometric segmentation models, this isn't a big surprise. But if you're coming from discrete computer science background, this might be a bit of a surprise. So this was kind of fun for us, MNIST. So that worked out really well. So here's our results on MNIST. So we're getting close to 97% classification. But the big punchline here is we're only using 3.6% of the data as training. So a very small amount we're assuming is known. And you might think you need to have some training, right? Because if you have no training at all, you don't know what's a 0 or a 1 or a 2, right? I mean, right? So you want to have something. So we're using a very small amount as training, and the rest is unknown, and we're getting quite good results. These are prior papers in the literature. A lot of these papers actually have no training data. They're unsupervised. But the support vector machine, actually, this example here is very supervised. It has 60,000 digits as training and only 10,000 as unknown. So these numbers are for a very different optimization problem from the one that we're solving with only 3.6% training. And there are other classical machine learning data sets that work quite well, and I have some examples here, COIL and WebKB, so those work well. Okay, a little bit of under the hood. Nystrom. So the idea behind the Nystrom extension, which is very, very useful for us, is the fact that our weight matrix, which is symmetric, can be approximated by a low-rank matrix, where you don't have to compute the whole thing. So the idea is that you have this symmetric matrix where there's a very large block here that you're never going to compute, ever. You're going to compute, so what you're going to do is random sampling, and you're going to sort your nodes into two sets, an X set and a Y set, and this is a small set, and Y is a big set. And so what you do is you compute this matrix, all of it. You compute all of this matrix too, the WYX. So these are pairwise comparisons between the set Y and the set X. But you never compute the pairwise comparisons within the set Y to itself. And so then what you do is when you compute, and by the way, this one is going to be the same as this because of the symmetry of the problem. So you compute these three pieces, and then we make this approximation, this low-rank approximation of the weight matrix here to replace this full matrix. And so this requires a much lower order number of computations, but it is a leap of faith that you can make this approximation. It seems to work very well on natural images, which are some of the big problems we're trying to solve. It also works incredibly well on real hyperspectral pixel data. I'm going to show you an example. So here's the hyperspectral example. So I love this data set because it's the biggest data set I have at UCLA that we can do machine learning on. This is a plume that's being released in the desert, and there's a camera that's about 2 kilometers away in Utah that's imaging the gas plume and all the background. So the background has a sky, a mountain, and a foreground, and a gas plume. But the pixels are not color. They're 128-dimensional long-wave infrared. Okay, so that's a tricky data set. So you can't see a thing because it's not optical, right? So you have to use the infrared spectral signature of each pixel to figure out what you're looking at. And that's a big problem in hyperspectral imaging. So we had fun with this. What we did was, this was Katie's part of her PhD thesis work. So she took some of the Nystrom so we took the Nystrom extension, and we took 7 video frames. That's 280,000 pixels. And we just took each pixel as a piece of data. We forgot where it lived in the image. We forgot the spatial location, and we just used the spectral information. So that's 128 dimensions, 280,000 pixels. In a minute or two on Justin's student laptop, we get 100 eigenfunctions. But you can then take the eigenfunctions and you can go back and remember where the pixels lived, and you can look at pictures of the eigenfunctions, right? So here they are. So you can see sky, something that looks like a noisy plume. I don't know what that is. Maybe that's a mountain. So Katie basically, by inspection, looked at the eigenfunctions and started thresholding the eigenfunctions themselves to pick out pixels that she thought had a very high probability of living in one of 4 different classes. And so she gave them, that was her supervision. It was hand supervised. So this is the training data that Katie got by playing with the eigenfunctions. And then she took the training data and she took all of the white pixels, which aren't training, they're unknown, randomly initialized them, and then ran the MBO scheme. And in a few iterations, she got this. It converged to this solution, which is about the cleanest we've ever seen for this. A lot of people have worked with this data set. It's one of the few US government data sets that those of us under contract are allowed to use freely with our students and collaborators from other countries. So it's a great data set. And this was done, by the way, the classification step seconds. This is done in seconds with 280,000 pixels. So in case you're thinking that sounds pretty good, let me just tell you we can do much better. So as of today, we are running all 300 frames of this video, which is, I don't know, about 13 million pixels, on one of the supercomputers at one of the DOE labs with about 30 nodes. And in like a few seconds, we can run this algorithm on that entire 13 million pixel data set with just one node on, so not the graph node, but compute node. So on Cori, which is an exascale-ready platform with 32 processors, in a couple of seconds, we can process 13 million pixels of this data set. So that's a result that's coming out in an OpenMP conference. We're just finishing today I was doing corrections before my talk on that paper. So that's pretty exciting because these algorithms are meant to scale well, and it's really cool to be able to take them and now run them on the supercomputer where we can really see that with optimization, they really can be scaled to run exactly like you would expect with a lot of processors. Okay, so that's great. Okay, this is just other stuff. Okay, these are, in case you're wondering, what about other graphical models? So here's spectral clustering on the same data set. And you can see that spectral clustering can find the plume, but it also introduces some artifacts in the sky. This is just k-means without the graph, so that's a very simple idea. These were just some comparisons that we did. And since I need to, let's see, I need to wrap up, so let me just mention. Okay, oh yeah, here we go. This is the stuff that's running on the supercomputer. So this is the urban data set, which a lot of people in hyperspectral will recognize. So there's a Walmart. It's a satellite image looking at a Walmart with some residential housing and trees and grass and things like that. So this is just showing what we can do with these graphical models. Let's see, so this one is the semi-supervised with 10% training data, and then D is unsupervised. We have an unsupervised version that's basically Chan-Vessey. It's this Chan-Vessey method kind of retooled for a graphical model. Yeah, so here we go. This is the OpenMP paper. So you can see the runtime here. And so you can see the overhead on the different parts of the calculation. So we're doing the Nystrom extension here. You can see the Nystrom extension had a lot of overhead in our original code right here. And then this is the graph iteration step. And by using a lot of optimization techniques on the supercomputer, we're basically able to take that Nystrom overhead and reduce it by a huge amount. And then you can see over here the scaling with the number of threads. So this is one processor all the way up to 32 processors. So we were really, really pleased with these results. Okay, so I want to mention just a few words about another unsupervised model, which is modularity optimization. So this is a problem that comes from the social network literature, looking at graphs that come from real social network problems and trying to do community detection within social networks. And so for community detection, there are a lot of methods out there, but one of the very powerful ones is called modularity optimization, where you have, it's an optimization model where you have a functional queue that you're trying to optimize over all possible partitions of your network, and you're trying to optimize this functional that depends on the weights and things that involve the weights. You can compute all these quantities from the weights. Okay, so that's modularity, and there's a discussion here of what it is. It measures the fraction of total edge weight within a community minus the edge weight expected if the edges were placed randomly using some null model. This is an idea that has been popularized in the network literature. There's several thousand papers on modularity in that literature. Okay, so what does this have to do with our work? Well, it turns out that modularity, this was a discovery we made with my student Hui Hu and Mason Porter, who introduced us to this problem, and Tamal Aran, who was a postdoc in my group. So the discovery is that modularity optimization is not approximately, but it's actually exactly equal to a penalized graph cut problem. And so therefore you can solve it using the methods that I've been introducing here. So here's the idea. So you can see that by you can't see it by looking at this, but you can see it by saying, wait a minute, if we think about all possible partitions, maybe we can subgroup them into all possible partitions with a fixed number of groups, right? So let's look at those subgroups first of the possible partitions. And so, for example, if you just force it to have 2 groups, then maximizing modularity is equivalent to minimizing this cut problem. So this is the graph cut exactly, and then there's a penalty term that depends on the resolution parameter from the modularity optimization. And this turns out to trivially generalize so that, so first of all, for 2 classes, you can rewrite this exactly in terms of the graph TV, because the graph total variation is exactly the cut. So there it is, graph TV. And then that penalty term turns out to be this term here, which is kind of a second moment, L2 second moment. So that's the minimization problem. But it turns out that formula holds regardless of how many classes. So 2 classes, n classes, you still have the same formula. And so once you fix the number of classes, you now have a simple TV minimization problem to solve. But of course, you have to solve overall possible numbers of classes. So for example, if you're given the 2 moons, you can give modularity the 2 moons, and you can say how many classes are there. Well, you can try different numbers of classes and see which one gives you the best score for modularity, and it's 2 classes, and that's the partition. And you can do 3-point clouds, and you discover that n equals 3 is the optimal modularity, and that's the partition. So it's really nailing these simple examples. So we decided to give it a harder example, MNIST. So we gave it MNIST, and we said, OK, here's MNIST modularity. Tell us how many classes there are in MNIST, and what is the partition. And modularity gives us the right answer. So here it is. So the first thing we did was we took the John Louvain code, which is not our code. That's another code for modularity. And we said, OK, here's the entire 70,000 digits. John Louvain, tell us how many classes. And John Louvain says there are 11 classes, and it took me several hours to figure that out. So you might say, wait a minute, we don't have 11 digits. I mean, I don't think, right? I'm counting, right? 0, 1, right? At least for me, there's only 10. So what did it do? So actually, modularity found the ones, and it splits them into 2 groups. So you have the ones that are sticks and the ones that have a flag, and those are 2 groups. But otherwise, it gets it right, and it gets it right with about 97% correct, which is absolutely amazing. So you can actually use, so the moral here is you can actually use modularity optimization, which was designed to do social network analysis for unweighted graphs. We can use it for weighted graphs for machine learning, for unsupervised machine learning without a known number of clusters. That's really amazing. But the problem is it takes a lot of time, right? That's really expensive. You don't want to wait that long. So what we can do instead is we can use our formulation, and we can say, OK, let's assume that we're only going to have somewhere between 2 and 20 digits. Let's not look for 50 digits in this data set. Let's only look up to 20. Well, if we do that, we can actually find the same 11 classes and almost the same accuracy, 96% accuracy, but look at the runtime, right? That's on the same computer. That's pretty amazing, right? It's the same kind of code, the same computer, and it's 2 orders of magnitude faster. And this one scales order n, and this one definitely doesn't scale like order n. So this is very promising because it's giving us some ideas now, because unsupervised machine learning problems tend to be hard. We do have some very simple methods out there like spectral clustering, but we also know that they don't work that well. And so, the hope is that maybe we can retool this idea into a new machine learning model that will work better on these graphical constructions. So I think I have to finish. So I'm going to skip. We have other work, but I don't have time. So I'm just going to leave this slide up and say that out of all these papers, if you want one to read, there's a Sigest paper that just came out a couple months ago with Flenner. And the Sigest paper is a republication of our first paper, but with a new chapter on all the new work that's gone on in the past 4 years. And so there's a ton of references in this, and all of these papers are referenced in the Sigest paper that just came out. So I'm going to stop. And thank you.
Hello, this is Takashi Matsuda, Kyoto University European Center. I'm not kind of the data science, but the data scientist. But I guess the talk is about the image processing type graph. And another type is the social networking type, like the graph just behind your kind of stool. So the question is how these two, image processing and the social network graph, the analysis or analyzing the dating.
Okay, so everything that I've talked about basically fits into one model. So, so the talk is about general machine learning problems where the data can be encoded into a similarity graph. So we have lots of examples of that. We can do examples from image processing, like the non-local means graph, which is this one here. Or we can do lots of other examples, like voting records, like MNIST, which are handwritten digits. So in the case of MNIST, each piece of data is one of those handwritten shapes. And you have to have, so in all of these examples, there's a bit of an art here, which is you have to have a metric that compares the pieces of data. So as an example, if I take the hyperspectral pixels, right? Each pixel is a 128-dimensional spectrum in the EM spectrum, right? So I can take that, and I really don't want to use Euclidean distance for those. Why? Because I could take one spectral signature and I could decrease the entire spectrum by a factor of 2 in all the different frequencies, and I would have essentially the same material I'm looking at, just not as many photons coming at me, right? I'd be looking at the same material. So what we did in the case of hyperspectral was we took the cosine angle between the vectors. And the cosine angle was used to calculate the weight matrix for that particular example, and it works quite well. And that's very well known in hyperspectral imaging as a good metric. So when you're doing similarity graphs for big data, you always need to have a very good choice of the comparison, and that's something you can play with. There's a lot of different features in this model. Yeah.
Any further questions?
Yeah, so in the Nystrom trick, the low rank approximation to the similarity matrix, I didn't catch how you choose X and Y.
Oh, that's a random sampling. There's no magic there. We do it as a random sampling, but we've started to try other approaches. So I don't think you have to do random sampling to get good results. I mean,
Can you do it better by choosing X wisely, or maybe iterating to get the right choice?
Yeah, so we've started to play with that a little bit, right? Because you may have situations where you want to preserve connections between certain nodes. You may have additional information for which it would make sense to preserve connections between certain kinds of nodes. So you can play with this, and there's essentially nothing in the literature on how to do that systematically, right? So that's an wide open problem. And even for us, we haven't done anything at all to develop this Nystrom code other than the new paper we're just finishing right now. We've come up with some very nice ways to optimize the existing Nystrom method, right, in terms of running on these big computers, right? So one of the things we're doing, I mean, this is very computer science hardware kind of stuff, right, and software, right? It's not really mathematics, but we're doing things like using the BLAS 3 instead of BLAS level 1 and 2 because of the matrix multiply aspect of those and the optimization of those algorithms. So that was a big win. We've also looked at, with the Nystrom and these different bins, we've looked at the supercomputers tend to put these things into chunks when they're doing the matrix multiply. So we've been taking advantage of the chunk structure on the hardware, right? In terms of how we kind of set up this calculation. This was the big overhead for us mainly in what we've been doing. So we put a lot of time and effort in the last few months working with Lawrence Berkeley National Lab to optimize the Nystrom step. But we haven't thought too much at all about the question you asked. It's a very good question, very interesting one. I think for somebody who likes numerical linear algebra, I will say I am not a numerical linear algebra person. I think there's a lot of people out there that could do this better than me. I'm not trained to do that. So, and if somebody wants to get into that and work with that, I will be a user who will be delighted to pick up on your work and try to use it in lots of interesting ways. And if there's people in the audience who want to go in that direction or want to hear more about this, I would love to talk to you after the talk, and I can tell you what sorts of things would be of interest to those of us who know the other side of these methods. Yep.
All right, let's thank Andrea.
Yep.